Let's talk about glass breaking. You've seen it happen 100 times. A cup slips from your hand and explodes into pieces on the kitchen floor. A baseball goes through a window. You tap a wine glass too hard with a spoon and suddenly there's a crack running through it. You've experienced this your whole life, so you must understand it, right? You know what breaking is. It's obvious. The glass can't handle the force, so it shatters. Simple, except here's what I want you to do right now. Explain to me exactly what happens when glass breaks. Not the superficial stuff. I mean, really explain it. What's actually occurring inside the material at the moment it fractures? Why does glass break into sharp pieces while metal bends? Why does a tiny scratch make glass weaker? Most people can't answer these questions. They think they understand breaking because they've seen it, but seeing something and understanding it are completely different things. And what's really happening inside glass when it shatters? That's where things get interesting. Here's what you probably think is happening. The glass is solid and strong until you hit it with enough force, and then boom, it breaks. The force overwhelms the strength of the material. That's the common explanation, and it sounds reasonable. But let me ask you something. If breaking is just about overwhelming force, why does the same piece of glass break differently depending on how you hit it? Drop it flat and it might not break at all. Hit the edge and it shatters into 1,000 pieces. Why? And here's another thing that should bother you. Take two identical glasses. Scratch one of them with a tiny diamond point, just a scratch you can barely see. Now apply the same force to both. The scratched one breaks at a fraction of the force needed for the pristine one. How does that microscopic scratch, that tiny imperfection, reduce the strength so dramatically? You might say, well, the scratch weakens it. But that's not an explanation. That's just restating the observation. What does weakens actually mean at the atomic level? And why does glass break suddenly, catastrophically, while something like copper bends gradually? They're both solids. They're both held together by atomic forces. What makes glass so brittle and metal so ductile? These questions reveal something profound. Breaking isn't what you think it is. Let's break this down properly. When I want to understand something, I don't start with complicated equations. I start with the right questions. First question, what is glass, really? Not the poetic answer, the physical answer. Glass is silicon dioxide mostly, sand, melted and cooled. But here's the critical thing. It's an amorphous solid. You know what that means? The atoms aren't arranged in a regular crystal pattern like they are in metal or diamond. They're frozen in a disordered state, like a snapshot of a liquid. That matters enormously, and we'll see why. Second question, what holds glass together? What keeps it solid? The answer is bonds, chemical bonds between atoms. Silicon bonded to oxygen, oxygen bonded to silicon, creating a three-dimensional network. These bonds are strong. Individually, each bond requires significant energy to break. So when you have billions and billions of these bonds holding the material together, you've got something pretty strong. Third question, if the bonds are so strong, why does glass break so easily? Here's where it gets interesting. Glass doesn't break because the bonds are weak. Glass breaks because it can't redistribute stress. Think about metal for a second. When you bend metal, the atoms can slide past each other along certain planes. Dislocations move through the crystal structure. The material deforms plastically. It absorbs energy by changing shape. Glass can't do this. The disordered atomic structure doesn't have slip planes. The atoms are locked in place. When you apply stress, the glass can't flow, can't bend, can't redistribute the load. So what happens? The stress concentrates. And here's the fourth question, the crucial one. Where does it concentrate? This is what Griffith figured out in 1920, and it's beautiful. The stress concentrates at flaws, at cracks, at scratches, at any discontinuity in the material. And at the tip of these tiny flaws, the stress isn't just a little bit higher than average, it's enormously higher. Hundreds or thousands of times higher. That's where breaking begins. Now we're getting to the real physics. Imagine you have a perfectly smooth piece of glass and you pull on it. You're trying to separate it into two pieces. To do this, you need to break the atomic bonds across some plane inside the material. How much energy does that take? You can calculate it. Add up the bond energies for all the bonds you need to break across that plane, and you get what we call the theoretical strength of the material. For glass, this theoretical strength is enormous, something like 14,000 megapascals. That's about 2 million pounds per square inch. Glass should be incredibly strong, but here's the problem. Real glass breaks at stresses around 70 megapascals. That's 200 times weaker than the theoretical strength. Why? The answer is cracks. Every real piece of glass has microscopic flaws. Surface, scratches from handling, internal defects from manufacturing, tiny cracks you can't even see. And here's what Griffith understood. A crack is a stress concentrator. Let me explain what that means. When you pull on a piece of material, you're applying a stress. That stress is usually pretty uniform throughout the material. But now put a crack in that material. The crack is a void, an empty space. The stress can't pass through the void, so it has to go around it. And when the stress goes around the crack, it concentrates at the tip. It's like water flowing in a river. When the river is wide, the water flows gently. But narrow the river, and the same amount of water has to flow faster through a smaller space. The crack tip is like that narrowing. The stress intensity at the crack tip depends on the applied stress, yes, but also on the crack length. And here's the killer. The stress concentration factor isn't linear with crack length. It goes with the square root of the crack length. A crack that's 4 times longer creates twice the stress concentration. This is described by what we now call the stress intensity factor, written as K. The formula is beautiful in its simplicity. K equals the applied stress times the square root of pi times the crack length. When K reaches a critical value, Kc, the critical stress intensity factor, the crack propagates catastrophically. That critical value is a material property. For glass, it's quite low, about 0.7 megapascal times the square root of meters. That means a tiny crack, just a millimeter long, in glass experiencing only 50 megapascals of stress will propagate. The bonds at the crack tip experience stresses far beyond what they can handle. They break. And once they break, the crack gets longer, which increases the stress intensity, which breaks more bonds, which lengthens the crack further. It's a runaway process. That's why glass breaks suddenly. But wait, I haven't told you the most interesting part yet. When that crack propagates, where does the energy come from? This is crucial for understanding fracture. You have a piece of glass under stress. It's storing elastic energy like a compressed spring. The material is slightly deformed, and that deformation stores energy. When a crack grows, it releases some of that stored elastic energy. The crack creates new surface area, and creating surface requires energy because you're breaking bonds. So there's a competition. Growing the crack releases elastic energy, but requires surface energy. Griffith's brilliant insight was that a crack will grow when the released elastic energy exceeds the required surface energy. He derived an equation for this. The critical stress for crack propagation is proportional to the square root of the surface energy divided by the crack length. This is why crack length is so important. A longer crack requires less applied stress to propagate. That microscopic scratch you can barely see, if it's a millimeter long, it's reduced the breaking strength by a factor of 10 compared to a pristine surface. This is why glass manufacturers obsess over surface quality. This is why tempered glass is stronger. The tempering process puts the surface in compression, so you have to overcome that compression before you can even start to propagate a crack. Now here's something that should make you think. The speed at which cracks propagate in glass. Once that crack starts growing, how fast does it move? You might think it depends on how hard you hit the glass. Harder impact, faster crack. But that's wrong. The crack propagates at a speed determined by how fast energy can be transported to the crack tip. And that speed is related to the speed of sound in the material. For glass, cracks propagate at about 1,500 meters per second. That's 4 times the speed of sound in air, faster than a rifle bullet. In the time it takes you to blink, that crack has traversed the entire length of a wine glass multiple times. That's why glass breaking seems instantaneous. It basically is instantaneous on human timescales. And here's another fascinating thing. As the crack moves through the glass, it doesn't just go in a straight line. It branches. It creates secondary cracks. Why? Because as the crack accelerates, it becomes unstable. The crack tip isn't perfectly sharp. It's rough at the atomic scale. Small perturbations get amplified. The crack forks, creating that characteristic pattern you see in shattered glass. The branching pattern, the fracture surface roughness. All of this records the history of how the crack propagated. It's like a fossil record of the breaking process, frozen in the fractured surface. Now, let's contrast this with metal. Why doesn't metal break like glass? The answer is dislocations. In a crystalline metal, the atoms are arranged in a regular lattice, and in that lattice, there are defects called dislocations. These are line defects where the regular atomic arrangement is disrupted. When you apply stress to metal, these dislocations move. They glide through the crystal on specific planes. As they move, the material deforms plastically. It changes shape permanently. This is yielding. This is why you can bend a metal wire. The critical thing is that this plastic deformation absorbs energy, lots of energy. When a crack tries to grow in metal, the stress concentration at the crack tip causes plastic deformation. The material yields locally. That yielding blunts the crack tip. It distributes the stress over a larger volume. It absorbs the elastic energy that would otherwise drive the crack forward. So the crack doesn't propagate catastrophically. It grows slowly, stably, absorbing energy through plastic deformation the whole way. That's toughness. Glass doesn't have dislocations that can move at room temperature. The amorphous structure doesn't have slip planes. There's no mechanism for plastic deformation. So when stress concentrates at a crack tip in glass, the only thing that can happen is bond breaking, elastic deformation up to the point where bonds snap, then catastrophic fracture, brittle failure. This is why glass is strong but not tough. Strength is the ability to withstand stress before breaking. Toughness is the ability to absorb energy before breaking. Glass has reasonable strength if there are no cracks, but terrible toughness because it can't deform plastically. Metal has lower theoretical strength but much higher toughness because of plastic deformation. You can also understand now why temperature matters. At very high temperatures, even glass can flow. The atoms have enough thermal energy to rearrange. Glass becomes ductile when it's hot. That's how glass blowing works. But at room temperature, the atomic mobility is essentially zero. The material is locked. Similarly, some ceramics that are brittle at room temperature become more ductile at high temperatures when diffusion and dislocation motion become possible. And you can understand why polymers behave differently. They're made of long chain molecules. When stressed, these chains can slide past each other, can orient, can absorb energy through molecular motion. Polymers are generally tough, not brittle. The molecular structure determines the mechanical behavior. So when glass breaks, what's really happening is a stress concentration at a pre-existing flaw, reaching a critical intensity that causes catastrophic crack propagation at supersonic speeds through a material that cannot deform plastically to arrest the crack. That's breaking. Here's what should really blow your mind. The crack that breaks your wine glass was already there, not metaphorically, literally. That microscopic flaw on the surface, invisible to your eye, was waiting. Every time you picked up that glass, washed it, set it down, you were creating and enlarging microscopic cracks. The breaking didn't start when you knocked it over. The breaking started the first time the glass touched anything. Every interaction with the world damages glass at the microscopic level. Every impact, no matter how small, creates or extends cracks. Glass is constantly on the edge of catastrophic failure. It's only the fact that these cracks are small that keeps the glass intact. The moment one of them reaches critical length under sufficient stress, it's over. And here's the kicker. You can't prevent this. You can't make glass without flaws. You can minimize them, yes. You can be careful with surface treatment, but you cannot eliminate them. The theoretical strength of glass, that 14,000 megapascals, is impossible to achieve in practice. We've tried. In the 1,000, 950 seconds, researchers made incredibly thin glass fibers, only micrometers in diameter, with pristine surfaces. These fibers approach the theoretical strength, but any macroscopic piece of glass, forget it. It will have flaws, and those flaws dictate its strength. So when you hold a glass, you're not holding something solid and permanent. You're holding something permeated with invisible cracks, any one of which could, under the right conditions, propagate at supersonic speed and destroy the entire object in milliseconds. The glass is always breaking, just very, very slowly, until suddenly it isn't slow anymore. This is what I love about physics. You start with something ordinary, something you see every day, and when you really look at it, when you ask the right questions and refuse to accept superficial answers, you find a universe of complexity. Breaking isn't simple. It's a competition between elastic energy and surface energy, played out at the atomic scale, governed by stress concentrations at flaws, resulting in supersonic crack propagation. And it reveals something deeper about materials, about structure, about the difference between strength and toughness, about why the world is the way it is. Glass breaks because of its atomic structure. That same structure that makes it transparent, that makes it chemically inert, that makes it useful for windows and containers, also makes it brittle. You can't separate these properties. They come from the same fundamental physics. Understanding one thing deeply connects to understanding everything. That's the beauty of it. So next time you see glass break, don't just see destruction. See atomic bonds snapping at the speed of sound. See stored energy releasing. See physics in action. See the universe revealing itself, one shattered piece at a time.